So last class, like we learned about initial values using different kind of methods like RK4, Euler, others, right? So today we are looking into some equations. What do you mean by coupled differential equations? That there will be just, yeah, two or more than two. Okay. So they will be of this type. So let's start. Simultaneous differential equations. Couple things up like differential equations. Lot of interesting phenomenon happening. So like there can be complex dynamics involved. So there can be chaotic dynamics. There can be very complex dynamics. I will not go into detail, but I'm telling you this ahead of time that if you have at least three coupled differential equations, the right hand side of the RHS of the dy by dx is non-linear, then your system is chaotic. Okay, what do you mean by chaotic? Like those things you can't normally predict. It's hard to predict, and the system is very complex. So that is one of your projects, okay, to explore those things like using Python, RK4. So we will see that in this simultaneous differential equation, suppose it looks like dy by dx equals to say f of x comma y comma z. Then you have another coupled equation dy by dx phi of x comma y comma z. Now, if you see these two equations, can you see them? Yes. Why I'm saying that they are coupled? If you f of x comma y comma z, the right hand side involves x, y, and z. Okay. But next, if you see dz by dx equal to f of x comma y comma z, it also involves x, y, z. So it involves one of the variable which is already in the first equation. That is y. So if y is changing, your second equation also. So they are not behaving independently, rather than they are depending on each other. That's how they are coupled, right? So it is known as a simultaneous coupled differential equation. You can have 4, 5 also, but 5-dimensional space, more than 3-dimensional, you can't really visualize, but you can take projections. Okay. So coupled differential equations. You only have say dy x comma y. Here also you have initial. And say z is another of your variable, z at x naught equals to say z naught, right? So we will see that there are a couple of methods, like there is a method like Taylor's method, you can look into it, but we won't cover it here. There is something known as Picard's methods as well. Okay? But our focus will be to of RK4, will be only on RK4. We will see that RK4 can actually be applied to this coupled system as well. It's not limited to only initial value problems. So we will start with our initial condition y naught and z naught. So our initial condition, if you see, is x naught comma y naught comma z naught. Okay, this is our initial condition. Now, how we will apply our RK4? For each of these x, y step sizes, right? Because last time, if you see, if you remember, we took our step sizes for RK4. Yes. So similarly, here also we will take step sizes. So these are our step size. Now we have defined our step sizes. Now we are ready to apply our RK4. So we see like further proofs and all those things, which is a bit complicated. I will just write an intuitive form where you can like solve the problems, at least computationally also. So this is one of the basic, I would say, basic algorithm or like method where you can try to solve coupled ordinary differential equations. Okay. Similarly, like if you remember, we had K1, K2, K3, and K4 method. Am I right? Yes. Yi plus 1 equal to yi plus 1 over 6 K1 plus 2K. Yes. Now we have coupled differential equation. For each equation will have its own ki's, right? K1, K2, K3, K4. Now your second equation will also have some similar sort of variable. We can't call them same ki's, so we can call them some other things. Up to you. I will call them L1, L2, L3, L4. Now I'm going to write it here. Let's see. So K1 will be, as for your RK4, F evaluated at those initial conditions. 5 evaluated at the initial conditions. How it is intuitive? Yes. What should be K2? X naught plus H over 2, comma, Y naught plus K over 2 plus Z naught plus, it's intuitive. But there is a mistake, right? Identify the mistake. This guy, K2 equals to F of X naught, Y naught plus K by 2. K, like we have the K as the step size, but we have to take, I think, your K1 here and L1 here. And it will keep on repeating. It will depend on the previous KIs and LIs. Okay with you? I urge you to look into the RK4 method again now. Let's look into it. Let me know if you find anything like, I already have it, so I will write it here. So similarly, L2 is Y naught plus X. Now when I write K3, like things will be different. F of X naught plus H over 2, Y naught plus K2 over 2. Yes, plus Z naught plus L2 over 2. Of similarly, you can write the K4. I'll write K4 and new page. K4 equals to, can you tell me if X naught plus H over 2, then Y naught plus, right? Similarly, you will have L4. Step. Now you are ready to find the yi and zi's. Okay. So you just have to do like, yes, we were doing, I think, we find y and z because they are varying. They are getting differentiated x. Yes. So for that, like you can say, like your next step of y1 equals to y0 plus then k1 plus 2k2 yes. Okay, so if I am right, like we have changed a few things here. So as you can see, H was missing everywhere, so we have added H now in blue. And this is our final. So you have to iterate this again and again, this formula again to get y2 z2, y3 z3, so on, till you reach your desired, till you reach your desired value. Okay. So y at your desired x or z at your desired x. So motivated by this, last time we were talking about some population growth models, like ecological models. We saw like, we considered a deer problem. That population of deer to like now, this time is suppose 2000. Then we applied, when we had a Verhulst model, the model only considered one population only, right? Am I right? Only X. So in that, 1 minus X over P. Okay. So that model gave us how the population of deers were varying in real world, right? Why? The model doesn't consider cheetah or tiger, which is already present in your model. Assumes that deer always live, doesn't consider the fact that there is a predator, which is a tiger which can eat the deer. So that is not accurate enough. So then scientists, new ecologists, new mathematicians, they came up with a new refined model where they considered the role of the predator. Now, if they consider the role of the predator, then things will change. Then it will be a coupled differential equation. Tiger depends on deer. Okay. Deer also depends on tiger. Am I right? Lot of deers. This is psychology of evolution. If there are a lot of deers, they won't get food. They indirectly want some tiger to eat the deer. Okay. So both are dependent on each other. Tiger is dependent on deer and the vice versa. So with this, start the model. So this is known as the Lotka-Volterra model. Two scientists, Lotka and Volterra, came up with this model. So they are saying that the governing equation is like this: dx by dt, x represents one of the population, ax minus bxy, then dy by dt dy by dt equals to minus of cy plus r of xy. Okay. So you have your initial conditions. X at time equals t equals to 0 is x. Y at time t equals to 0 is y0. As you can see, the population of x and y, they are varying with respect to time. A, B, C, and D are actually your parameters, and it is within your control. What you will have, what you will set. So these constants are actually meaningful constants. They are just not any constants. They Y as the predator. From ecology point of view, like A, B, C, and D, A and C actually, A and C, they represent the prey growth rate, prey and predator growth rate. Okay, are the interaction parameters. How predator is interacting with the prey, and how is prey interacting with the predator. So A and C, I would say, they are like prey growth rate. Then I can say B and R to be like the predator prey interaction. Yes. Now our aim is to solve this Lotka-Volter equation of population dynamics. Both, um, if I want you to know that this is not that much solvable analytically. Even if you see, it is not that complicated. Tiny linear x and xy terms are there. The xy term is the nonlinear term. There is one other variable which is changing with respect to time. Okay, then it will be a three-dimensional equation. Then it will be highly complex system. Okay, one of your project, as I already mentioned. Okay, can we solve it analytically? Let's try to solve analytically. If it is not possible, we will go to computation. Can we solve analytically? I think dy by dt by divided by dx by dt. Then you will get something like dy by dx. Dy by dx. What is dy by dx? Plus. Then can you solve this analytically? That's the question. High school knowledge of differential equations. Can you actually solve this? Um, so just something like this, you can rearrange in this form. How to solve it? From this, once you integrate, start integrating, you can log term will be coming in. Yes, am I right? So from that, like yes, if you see my notes, you can see that it is written like this. Check it again. If you put x naught and y naught as your now, it is obvious that I don't think there is a well closed form of this. Can you separate y totally from x? Can you write y equals to something? Observe that y is there, linear, then there is a log y term. So it is pretty tricky to just them, like just make them separate. Analysis can only take you till here. After this, you are stuck. So after this, how you will solve it? That's the question. This equation, does it provide any qualitative information? It's a bit complicated to provide any qualitative or quantitative information. Always you can plot this, no doubt. You can plot y versus x, but then you are using computer. I am asking. calculation? Can you get something, some information? So therefore, like we need to move towards the computation. Okay. So I have like we have simulated this in Python, the same coding. Start. So this is the code for the Lotka-Volterra model. As you can see, I have imported NumPy, Math, and Matplotlib pyplot. I am first initializing or setting up the parameters A, B, C, and D. Yes, as you can see, these are just the parameters. You can take your own. A I have set just 1.2, B 0.6, C 0.8, R 0.3. T naught is 0, time t equal to 0. S naught, X naught equals to 2, and Y naught equals to 1. These are the two population. These are like the non-dimensionalized version of the population. So 2 may imply 2 lakhs. 2 may imply 2. Scaled it down in order to avoid large set of numbers. And n, like, yeah, the number of time steps I want to divide in between 0 to 30. Okay. As you can see, h I have set here tn minus t naught by n minus 1. So these are the time steps. And x and y are the same, are the arrays of the same. I hope you understand the logic behind this. The reason is for each time instant, there is for each time instant, there is a predator and there is a prey. That is the basic idea. So therefore, the size of the T array, X array, and Y array should be the same. Better instead, because you can set it to be like a dynamic array, like just like that. You don't define any. But since I already know the size, it's better to define it. See, and also to avoid any random numbers anywhere, I have just set to all to 0. So T, X, and Y are the arrays of only zeros in them. After that, what I am doing? I am defining my two functions. As you can see, this is the fx and fy. The x component of fx, the y component of dx by dt, that is the RHS of the RHS of. Is it correct? Ax minus bxy and then minus cy plus. Just check your notes again. Have we wrote the same equation, or there is a plus minus sign mistake anywhere? I'm doing. After that, what I'm doing? I'm defining the K1 and L1s. Just I have defined, like, for smoothness, just I have defined KX1, KY1, KX2, KY2, KX4, KY4. Just like K1 to K4, L1 to L4. Just different name. First, we are doing KX1 equals to f of fx and evaluating at the initial step. KY1 evaluating at the initial. KX2 is f of x, then ti minus 1 plus h over 2. Now it is depending on kx1, you can see, which is evaluated previously. Y1 was also evaluated previously. So in that way, kx2 is depending on kx1 and ky1. Y2. Okay. So ky2, you can see, yes, is almost the same as that, but yeah, kx3, ky3 depends on now kx2 and ky2. kx4 and ky4 depending on kx3, ky3. After that, you are ready to define your output. That is the value of x and y. Xi equals to xi minus 1 plus h over 6 k1 plus 2x2 plus 2x3 plus x2. Similarly for y, okay, and you have to increment your time. We don't have that, so you have to increment your time based on the step size h, and the loop continues for n number of steps. That is 301 I have set here. You can set as much as you want. Why I have set 300? Within that I am getting the output already. So why to iterate it more? Plotting it. What I am plotting? T comma x. What does that mean? X is varying with respect to time. What it is known as? Time series. I think you are having an open elective on time series. No? Okay. So there you should know that it's a time series analysis. It's a completely different course. But yeah, how things are varying with time. There we will have only the data with us. Now the data is coming from a coupled differential equation from an ecology perspective. But in time series, actually, you will have the data of how things are varying with respect to time. You will directly start with data. So I am plotting the time series of x and y. Then after that, I am plotting x versus y. So try up to this point. Right. So after you plot this plt.plot t comma x, you are plotting the time series of x, and plt.plot t comma y, you are plotting the time series of y variable. One of them is prey, one of them is predator. Then I am giving the legend like yes, predator and prey. Not a good place actually to put the legend. You can vary that LOC legend in at different positions. Just try to find a particular spot where it is free. Maybe I could have kept it here somewhere. Now it is obstructing the data here. Blue is the prey, this is the predator, the orange. And they are having this kind of time series. It's an oscillating time series. So predator and prey populations are not staying constant. Rather, they are oscillating, which happens in real world phenomenon, right? You normally don't see the population of tiger just 10,000 throughout 5 years. They keep on decreasing or increasing. So dynamics of population, like population dynamics, school and ecology perspectives. Through these kind of modeling, they come to know whether one of the species has, is endangered or those kind of terms. Now what I did something else. I plotted x versus y. I have not given x label and y label, but what I did is plt dot plot x comma y. After that, I am seeing this just a nice, so what is that figure? So this is showing that each population is oscillating. You won't get this figure if one of the population is steady. Both of the population are oscillating. Therefore, you are seeing this kind of figure. So technically, these are known as limit cycles. That's another branch. It is linking to another branch of dynamical systems. Is like it is dynamic. Those systems which are dynamic and vary with respect to time. So the population dynamics is one such example. This is just one phenomenon. One of the project is Lorentz system, where I expect you to get very nice butterfly effects and all those things. So this is one of your projects. Okay. So we considered like previous classes, we are doing initial value problems. What are initial value problems? Those differential equation where the initial state is being specified to you. And then you are using time step and you're using a numerical method scheme to march forward towards a final x naught value, desired x naught value, where you want to find the y value. That's the idea. And we are using the Euler method. We are x naught, then x naught plus h, x naught plus 2h, so on till the final variable. Now there are other kind of problems where you have the initial value specified, but specified at the boundaries also, right? So there will be the values will be specified at the boundaries of the region. Usually your solution is, now we are doing dy by dt, dx by dt, where these x and y variables are actually defined. They are defined on, since these are predator and prey, they will be defined on the positive real axis. Am I right? Because negative population can't be negative. They can be at most 0 or more than greater than equal to 0. So therefore your, so here also in any kind of or differential equation, or where you have x, y, and z, if suppose you have x and y coupled equation, then you will have a region, or like a region, you understand? Then you have a boundary, you have a region. So those, the values are being specified. So therefore those kind of problems are known as boundary value problems. Okay, in a volume where the points are specified, the values are specified at the boundaries of that surface, and your method, which you will be learning now, two kind of methods, and it will predict the, not predict, like it will compute the values of that function at the nearby values where it is not given to you, and that is unknown. So here, like, yeah. So therefore, in these kind of problems are known as boundary value problems, because your values are being specified at the boundary. One such thing. So solving a first order ODE, usually you only need, to get to a particular solution, you only need one constraint. Okay. Now, if you have nth order ODE, like coupled order ODE, like more number of equations, then you will have that many number of equations given to you, that many set of initial conditions given to you to solve it. If you are being given, see, if you are being given prey model, dx by dt and y0 to you, therefore it is solvable. But if I would have specified only x0 and not y0, would it have been solvable? Don't think so. Therefore, like, you need to have, how, if you have two sort of differential equation condition, boundary conditions, in order to solve it. So yeah. So usually the boundary conditions, so these are known as boundary value problems. So in a boundary value problem, like, there are many different cases you can have the values. One, suppose like you have the, I'm considering the right hand side of the derivative x, or x, f of x comma y, these things. So either fx values, fx specified in the two boundaries, at two boundaries, okay. Suppose your boundaries are x equals to a and x equals to b. That means f of a and f of b are being given to you. You know those values. Other thing might be possible, the derivatives are given at those boundary points. That means f dash a, f dash b is known to you. Then it is also a boundary problem, boundary value problem. Third, mixed conditions are being given to you. What are mixed conditions? F being given to you, f dash b is being given to you. That's a boundary value problem. Or f of b is being given to you, f prime a is given to you. So all these can lead to boundary value problems. This class we will be looking at two different methods which are very intuitive. The first one is known as the shooting method. Okay. What is the shooting method? Has anyone covered shooting method before? No. Not during BSc. Okay. So the idea is now whatever we have learned for the boundary value problem, we will apply whatever we have learned so far. Only those things we will take again, right? So here the idea is, the basic idea is we will transform the boundary value problem, which I will start calling it as BVP, right, to set of IVPs, like the initial value problems. So the idea of this method is whatever boundary problem is being given to you, right? This is one of the method. There is another method known as the finite difference method. So idea is like you will apply the finite difference approximations whenever you see derivatives, and the idea will be to transform the boundary value problem set of simultaneous to solve. All right. So you will have lot of equations, like lot of simultaneous equations, which you need to solve in order to get those values out. So these are the two methods we will be covering. So one of the main question is why we cannot proceed like the method is. Why we need to learn two new methods? Adding pain. So why don't we learn the methods we have learned for initial value problems and just apply them here? The only reason being, in initial value problems, you can start at the initial value, okay, and then march ahead with your time step, keep on iterating, and you will generate more and more values to get the solution. But in this method, that process won't work. Why it won't work? Initial conditions to solve that ODEs. That's the only demerit. That's the only demerit. Why? Can you see why here? See, fx is specified only at two boundaries, fa and fb. But you can see that in the first boundary, one of the variables are missing. So what about like its derivative there? We don't know any idea about it. So the ideas of these methods will approximate. The shooting is like, so I can tell you on the game, I think I hope that most of them have played in their childhood. Like you have these glass marbles, you keep it there, and then you try to aim one of your marbles to hit that. Yes, goli, I think. Yeah. So those kind of, yeah. So how you are actually in that kind of age, you are already applying the shooting method. Now you are learning the shooting method, how to do it in math. But indirectly, you are applying shooting method at childhood already. Okay. So yes, after the break, we can do it.